right. We are so far ahead that I don't even know what to do with myself. It's a good place to be. So I need to get you your last assignment and your last project. Those will be coming probably at some point today. But we have our third exam this Friday. So there's a study guide out to help you prepare for that. Asterisk time at the end of today, there will be. I'll start going over some practice problems for exam 3, and I will have our official review on Thursday, but I want to make sure that that is timed solely for you. Since we have a little bit of flexibility and extra time, I can take that whole day to your questions instead of your questions, and as backup, I have some more problems. We'll get the problems out of the way this week, and then whatever questions you have, you can take up as long as you want. Questions before we dive in? There's a ton left to cover. Last time we were talking about making a DFA representing the LR parsing stack. We discussed the concepts of items and closure. Items being right-hand sides of productions where there is a marker somewhere in that right-hand side. Everything to the left of that marker is on the stack. Everything to the right of that marker is on the stack. But if it were to be on the stack, then we could do a reduction from the right-hand side to its equivalent left-hand side. So we looked at that and we started doing an example. We said as the start of this, we begin by adding a new start symbol and a new production that leads into the start symbol, which is strange, but it's necessary in order to get this to work. So we number our productions, including this new production, as new production 0. We created a start state, and we calculated the closure of the dummy production that we added, and that became our initial state. Then we expand that state by figuring out, okay, what of these aspects, how do we move forward each of these? So we need to calculate the associated closure of each of these. And then from that closure, we can make transitions out of this on what we can do with regards to moving past each of those dots. So move the marker over S. Closure of this adds nothing, so we make a new state and associate it. Move the marker over every terminal at the beginning of each of these, and that allows us to make a transition on that character. And you continue to do this until we hit, right as we ended, this is kind of the partway point where each one of these is now a new state representing moving past each symbol at the beginning of the set of right-hand sides from state 0. We put a transition edge with the label of the character that we move past. Were there any questions on this midway point? Or how we got there? Take some time to stare at it in case anything doesn't make sense. Very bouncy.
Yeah. I suppose they could be tap dancing in the room directly above us.
It sounds slightly more fun than this.
I think I get it. I mean, I definitely don't get it well enough to actually implement this algorithm, but since I don't think that's a requirement,
Yes.
I'm okay with that.
Yeah, so what happened is we went from Q0 to Q2, for instance.
Right, yeah, you consume a single A, and so that changes what productions you could be looking at, right?
Yeah.
Basically.
So from here, this transition is based on this reading past this A from this production in Q0. As you read past that A, we get this. So that's moving past that A. But since the marker is right before a non-terminal, we now need to add the closure of this non-terminal to this box. So that basically is copying everything, these four from here, which is the closure of S, and copying them right here.
Right. Right, because that kind of maps to how.
Yeah, we have to move past that S. Now here, to be able to get past this S, it's the same thing as having to get past that S, but being on this, having gone down this transition, then we know we're past this A in that, but now we need to get past an S, and to get past an S, we have to see one of these possible ways to reduce down to an S. So those are just the transitions out of Q0. How do we feel about that?
Why don't we do the state date for? Oh wait, no, never mind. I was looking at only Q3 for S to A.
Yeah.
Pathway.
Yeah, each one of these transitions maps to moving past one of these characters, which is why there are 1, 2, 3, 4, 5 more 1, 2, 3, 4, 5 more successor states, because they're over different characters as well. Capital S, lowercase a, capital A, lowercase b, lowercase c, all different characters. Otherwise, there would only be a transition for each different character that we saw. So we now add a queue of states to expand. So everything that we haven't yet expanded, we need to expand. So we expanded Q0, we need a queue now of all 5 states that we just added. States 1, 3, and 5 are simpler than states 2 and 4. 1, 3, and 5 only have one element associated with them, so there's nothing to expand. You add the closure of the next character. But since we moved past a capital A or a lowercase c, etc., then there's nothing to expand there. There's nothing to add to the closure, so nothing needs to be done. But states 2 and 4, on the other hand, by getting there, there was the next closure to add. So expanding state 2 creates 5 additional states, but some of them have the same elements in their sets as existing states, so we can remap back to existing states. Similarly to how we saw this when we converted an NFA into a DFA, we found that the exact set that we had created was already there, so we could just make an edge from the state to the state that already existed because the same elements were in their sets. And yeah, you just continue to doing this to each state that is added until we don't add any new states. Once we do that, we are done and we find the full structure. But we should now figure out how we could determine this with this. So there is an example. Starting to need to replace my markers again. It's that time already. Let's say start at the state, start state. Yes, 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 yes. Do we have an example? Yes. It's our good old friend ABCAB. So let's actually go do this. So the string we're trying to trace is ABCAB. So we start in Q0 and we want to read this A. How do we do it?
Using the DFA or
Using the DFA.
grammar? Oh, well, I mean, I just follow the edge labeled A.
Yeah, follow the edge labeled A, that gets us to Q2. So we read the A, taking us to Q2. Now we want to read a B. Where do we go? There's an S here, an A here, an A here, a B here, and a C here. Well, the B is right there. So we can follow the B edge label and get down to Q4. How do we read a C? So B, sorry, that's capital A, B, and a C. So we can read the C directly, going to Q5, reading the C. So what is on the stack at this point is we are adding these to the stack, doing the equivalent of adding these to the stack. So we would have, at this point, a Z, an A, B, and a C on the stack. But this C can be reduced directly to an A. So by moving backwards from Q5 back to Q4, we can turn this C into an A. That defines what this does in reverse. Once we have that A, we can move forward past this A in this item. So we're going to do that, moving here. The A is already on the stack. Then we can add the next A, because that's what comes next. So now there's another A on top of that. But now what's on top of the stack, we know because this item is associated with this, in order to be in Q9, we can do a reduce, and that reduce is the BAA that is on the stack that has to be in order to be in that state of the DFA. So we're going to replace all of the BAA with a capital A. And that reduce here is going to be moved backwards over the A, the capital A, and the B, all the way back to Q2, so that we can move past an A. So this allows us to move past this A, which tells us that this A can reduce to an S. If we follow that A to Q3, then having moved past this, this can become an S. So we move back here, and now can move forward past this S, which takes us here. So then we just move down, shift down the last B as the B that we need to read in order to move here. And we see that the ASB can now be replaced with an S. So we do that. We can do that reduction, giving us this S. Moving backwards over the B, the S, and the A, taking it all the way back to Q0. Now we have the S on the stack that we can move past as we move to Q1, which is our true final state. Saying that we move past this, we can now halt and accept that this is in this grammar. It's in the language that this grammar would have represented, but now it's in DFA form.
Interesting. Okay, so like every time you reach a final state and you apply that reduction, then the next time you consult the DFA, you're one state behind. So it's like you're in the previous state, the state you were before.
It's one for each of the symbols that you reduced to.
Oh.
So like for instance, the ASB, I guess so the BAA that we were in here, we had the C, we moved to an A, we moved past that A, and we ended up here. There are three symbols, A, capital A, B. So you're going to move backwards the A, the capital A, and the B. But you have to store where you came from, because there's also a B here. So there are two B edges in here. Which one did we end up with? We now need to know in order to be able to move past an A, how to do that, because now we can move past the A here.
Is it also true then that basically it's like the DFA is reading the contents of the stack? That's how you're moving? Okay.
Yeah.
Okay, yeah. So the DFA isn't directly reading input, it's reading the stuff in the stack.
Yeah.
Okay, I think I get it. Or I get it more.
Yeah, it's what's going to remove the ambiguity as you go through the LR parsing process where you are building up the stack. It's just that when you are in particular places on that, you will know exactly what you need to do. You take this BAA and you move left, 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 given the stack. So you're going to store tuples of the character that you read and the state that you were in when you read it. And that will tell you where to go back to. Let's actually get that example, because that is what's coming next. It's drawing it out in that form. And if we use this as a guide or a reference, then there is no ambiguity between a shift or a reduce. There is always something that tells you where to go and what to do. So yes, start at the start state. It's just going to go through words of what we just went over. Repeatedly apply, shift and reduce. Shift moves forward in the DFA. And the reduce moves backward in the DFA for each symbol in its right-hand side, then moves forward based on the left-hand side. So shift directly moves past a terminal, and a reduce moves backwards in the DFA to create the non-terminal, and then shifts past that non-terminal, moves forward past it. Go. Any item in a final state with a marker on the far right side is possible for a reduce. Everything done so far. Yeah, to know which state we came from for that ambiguity of like two edges coming in with the edge label B, then we also have to push the state numbers when we do any kind of forward transition to say where we came from so that there is no ambiguity when we're trying to backtrack. Yeah. So let's do a full LR1 parsing example using that. And so you end up, it looks exactly like what we just did, but this is one way to envision this as being tuples. You push on the state number and the symbol, but I prefer to think of them as actual tuples and not individual characters. So you have an object that represents a tuple, and when you push on a tuple. When you pop off a tuple. So here is, from the textbook, the exact full description of what is done. Sometimes I like to augment my own examples with something straight out of the textbook in case that I feel like the step-by-step is useful to be there. This is one of those times. But you will note that because of the look ahead, because of the action, because of the DFA, there is no ambiguity on what to do here. We can parse this in linear time because there's no search that has to be done to determine between shift and reduce. There's always a correct answer. Any questions about this?
So it is necessary to record the state you were at, or could you? So you can't reconstruct which state you were at by just looking at the stack.
Right, yeah, if we look back at our example, there were two edges coming into Q4 on a B from here and here.
Oh, okay, yeah.
So if we're trying to go back the A, capital A and B, we move back the A, the capital A, and now do we move back to Q4 or do we move back to Q2? It's ambiguous. But if when we moved past this B in the first place, we stored a B and coming from state 2, then we would know when we got back here, we would see the 2 associated with that B to know to take the edge from here that moved back to Q2.
Okay, well, I guess my thought would be that if your reduction takes you back to Q4, and then you use up another B, wouldn't you still have either just like the single A or the single B on that stack telling you, oh, you we went to Q2 or to Q4.
It looks ambiguous to this from my perspective. You would break in Q4 if you tried to go back there because the V capital A becomes an A. And you actually already moved past this A. So it would be an error really to say that, hey, we reduced this to an A B is still on the stack after the B capital A, which is not the case. This would lie to us. So it only really works if we come from where we actually came from. We go back to. Other questions? This is really good so far.
Now you mentioned
Yeah.
that there are still context free, like there's still situations in which this can't parse grammar sufficiently, right? And we
Right.
still need to use CYK.
Yep.
Theoretically, instead of having a DFA to use a PDA, what if we have a PDA also inside the PDA?
It turns out to not tell us anything new, which is unfortunate, because that would be fun. If not just the laws of math saying, in case you hadn't studied recursion before, here it is.
Yeah.
But no, it doesn't really give us any real new computational power, adding a stat here instead of a DFA. The DFA is really all we need. It's going to be finite size for any given grammar that it can parse. And you can see though that the issue with it is that you may just continue to expand and expand and expand and expand. There's no bound to the size of the DFA.
Yeah.
Right, yeah, 'cause this is like, it's only looking ahead one character, so
Right.
an LR2 is probably.
Yeah.
But what we call characters here would be tokens in an actual language, right? They would be
Right.
like actually much larger,
Yes.
so. Okay.
Yeah, the question is how many tokens would you need to look ahead in order to continue forward with a linear time parse? But the fact that we know, the fact that we can think about, and that shows me that we're ready to write a compile. If there were a part 2 to this course, we would be ready.
So why isn't there a part 2 of this course?
That's true for just about every course that's out there. I would want there to be a part 2 to just about everything. There's only so long. We got to get you out and making money. I know, right? It's so disappointing. I just want to accrue more and more debt for my entire life. I want to model it off the United States of America, in which I am a citizen.
They can do it, why can't I? Like,
Yeah. Well, I think the key difference is they can print money.
I mean, we
I'm not
technically could as well.
as long as they don't catch us.
Exactly.
Don't steal. The government hates competition.
All right, so we talked about this, we talked about the example. Yeah. Each final state only had one item in it, a single reduce, but it is possible to have a final state with multiple items, some of them having the marker at the rightmost position and some of them not. So it would be a final state only for the production for which we could reduce, but we may be able to move forward from there in other cases. So in this case, we would still have to choose between a shift and a reduce, which tells us that it's not LR1. So yeah, look aheads can help with this, but not in all cases. If we use a look ahead of size 2, then we can remove that ambiguity between a shift and a reduce. No, this actually shows us how to go about that. Yeah, especially where lambdas are involved, that becomes very challenging. And LRs do not handle lambda particularly effectively. In some side cases, we can do it, but in a lot of cases, that leads to further problems that CYK needs to solve. And we did it. This is the single last slide that I had prepared for this course. And every time I teach it, it feels like it's becoming earlier and earlier. I don't know if this says something bad about me, like it's become so obvious to me that I teach it like it's obvious, or if I've just streamlined the process so there's less dead time, or if I really should be allowing people a lot longer on their practice problems. I don't know, now that we've been through the class, anyone have any feedback of how did this pace feel? Did it feel too fast? And if so, where would be an adequate place for you, for me to have slowed down?
I think I just should have studied more. I think just getting the grades back faster would have helped more with that, getting faster feedback, and then I can realize, oh, I need to like really study.
I'm actually working on that with a student who I had a year ago, who has since graduated and is interested in making a Canvas plugin solely for this course.
Oh, really?
Wow.
That would be able to take as input a kind of like a JFlap export
Okay.
that you could then write unit tests for, that you could very easily cut down on the grading time for a course like this. So that's a really cool project.
Cool. Yeah, and I mean, I'm sure the way you teach it is probably the best way, but I did have a random idea the other day of like, well, what if you just sort of like threw the DFAs and NPDAs and Turing machines at people all at once right off the get-go, but just gave them very simple problems, and then like the next homework was more advanced problems. The next homework was like introducing non-determinism. So it's like you're getting familiar with the machines, like studying the same machines throughout the quarter, just on a deeper and deeper level. But that was just
Interesting.
like, I don't know, just an
That
idea.
is very interesting. Yeah, where is the complexity? Is the complexity in how fast you need to know rules, or in how deep you need to understand how those rules can create complexity?
Yeah, because it's surprising how like with the same, it's like you're working with the same kind of automata, and it's like going back to build an NPDA for like A N B N. Now build one for A N B N such that, or A N B K such that K is less than or equal to 2N. It's like, okay, well, the second problem, it's like there's a serious like bump in difficulty there, or another problem where it's like such the star closure of A, B, and C such that A, N, B, K equal those little extra rules. It's like, oh, it's the same thing, but a lot more challenging.
Other thoughts? What would have worked for others?
I think the only thing that I really struggled with, like largely speaking, because the content clicked for me a lot of the time, it was just I didn't spend enough time doing the homework and preparing. So kind of like you, like I just need to spend more time studying. But it just like this is all just so interesting to it. I'm just kind of like I kind of wonder what the next step is as well. Like I'm just curious as to where to go next, but there's not enough time for that as well.
The next step would be to dive in and actually make one.
Yeah.
And I pulled out the two projects that are reasonable in complexity, but also reinforce concepts from earlier and reinforce concepts in case you don't go into building a compiler for a living. I still want this course to be meaningful.
I think one thing I really enjoyed was the Veritasium video, and I think maybe getting like one or two lectures in there that just do sort of a review and a high level, like this is the Chomsky hierarchy. These are where these machines are on the hierarchy. These are like the sort of restrictions on grammars that are lifted as you go up the hierarchy. Like this is how it all ties together. Getting a little bit more of that, even if it's a little redundant, like you're doing it kind of like every other week in the quarter, you're doing something of a review and how all this stuff connects together. I enjoyed that, a higher level view.
Yeah, it's fun because a higher level view of the content that's a higher level view of the what you've been majoring in for the last few years. It really is the toppest level view, the highest level
Yes.
view,
Yeah.
looking down on everything you have seen to date. These data structures and algorithms that you've been learning are all represented in a Turing machine for
Yeah.
making it easier to do complicated things within this structure of how a machine works at an algorithmic level.
Yeah. And especially like, I don't know, it is kind of a mind-blowing realization. Like there are some problems which like don't really have an answer to, and you don't even know if you have an answer to it or not, because it's just going to keep spinning forever.
Yeah.
That's a fun.
Anyone else have any insights into, especially given this is the earliest that I've kind of run out of this, I will find something to talk about. And that's something that we will talk about today is what do we want to do with our remaining time? What deep dive do we want to take? What do you feel like you've been missing from other courses? What do you feel like you want to do with your CS education that you haven't had a chance to really dive into or look at? Or how can we find a middle ground between my expertise and what would be useful to all of you? So that's what I want to do with a little bit of the time that's left. I think that's not good to start today, but maybe spend a day or two thinking about that. What could plug some holes that are leaking just from past classes of just, I know there's this material that's out there that I should know, but I don't feel as confident in it as I would like to. Because otherwise we can just work on caddis problems or leak code problems.
That'd be fun.
We could implement some almost interview style, solve this kind of problem in a reasonable amount of time using the tools in your toolbox. Let's think about it and solve it. Go. So we could do that. We could do a deep dive into, I have experience with AI and machine learning. I have experience teaching design patterns and object-oriented principles. I have experience teaching some software engineering. I have experience in games,
I guess the better question is, what do you not have experience in?
I haven't taught a ton of architecture or operating systems. I don't have a deep dive in databases, but I have enough to be able to cover kind of the data science approach to what happens when you have a ton of data. I have some experience teaching computational biology. Advanced algorithms. Theory like NP completeness and reductions.
Well, I think for sure doing some review of like pumping lemmas, something I would like to do.
Yeah. There is a practice problem prepared for the context-free pumping lemma.
Yeah. But in terms of like those advanced topics, shoot.
Yeah.
It's like there's so many.
There are a lot.
Pick.
I don't expect people to have an answer to that immediately because it's going to be a little longer of a meditation on your part to try to figure that out. But have that on the back of your mind, and maybe I'll ask you at the start of tomorrow's class.
Okay.
In the meantime, there is certainly some practice that we can do. Right. Let's start with designing some Turing machines.
Oh boy. Remove the first A.
I like these to be similar in complexity to exam styles of questions so that you're getting a sense of not only can I solve these questions, but can I solve them in a reasonable amount of time? So the goal here is not to create incredible complexity, but the goal is to give you a reasonable exam style problem and now say, can you have the moment of brilliance that pulls this together reasonably quickly?
Just as a quick question, say the string is entirely made up of Bs. We do nothing to the string, right?
Correct.
If there's a bunch of B's and then an A and then a bunch of B's, do we have to shift those B's to the
Yes.
right? Okay.
Yeah, we want the output to be on the tape when we are done. This does not say that it is a one tape Turing machine. So you could have an output tape, and you will find this to be the case usually on exams, unless it states a one tape Turing machine, which I reserve the right to do.
I mean, then if you have two tapes, then the answer is relatively simple because you just walk through the first tape
Mhm.
and you just copy whatever's on the first tape to the second tape until you see the first A. And then you stay on the second tape
Mhm.
and delete it from the first tape. And then you just continue copying for the rest of it, no matter
Yeah,
what.
so you need a second state.
Two states, like
Yeah, state zero,
transitions.
read past all of these, copy them over.
In a single tape, I can see it being a little bit more painful, but that's only because of like the shifting of
Yeah.
the characters.
Yeah. It might be worth trying to design it as a single tape Turing machine. This is a good practice problem for that because it's not terribly challenging to do on one tape. It is still harder than it is on two tapes. So if this showed up on an exam without that one tape requirement, I absolutely would design this as a two tape Turing machine. Save yourself the time.
I think you could do it with 4 states on one tape. What I've got here, I think there's a way of reducing it further, but
So state one scans so you see the first A. State two will move forward to the next symbol, store it. So we'll need a branch there for whether that stored thing was an A or a B. Move back, replace the stored character there, move forward and then reset. So that also has it in 4 states, except for the final accepting state when you see it in blank.
oh shoot, well I hadn't thought about like, I guess I do need to add halting state, sorry. No, I guess for the case where there is at least one A, and I think this should work. The first state is just scan A. As long as you see a B, move right. When you see an A, write a B.
Do we know that character is a B? But if the first A is immediately followed by a second A?
Well, we're only trying to remove the first A, right?
Right. So why would you write a B? When you see the first A, if you write a B, you're assuming that what's coming back from the character ahead of it is a B.
Well, it
You want
should
to write whatever that next character is.
remove the first A. Well, I'm thinking. Oh, okay. So if the A is the very first character, if there are no B's before the first A, because I was thinking you just sort of like, if you have a certain number of B's, then you have an A, make this a B, and then you go back and erase the first B and make it a blank. But if there are no leading B's, then yeah, it's gotta remember what the other character was.
Interesting. Yeah, if there are leading B's, you can't just delete the first B and move that to the first A, and it will do the same. But yeah, if there are no leading B's, then you would delete the first A.
Which then,
Same.
yeah,
There's something there.
Well, I mean, it works in one case. But...
Yes, I think it might work. You have to have 2 separate states for is the first character a B or an A. If the first character is an A, delete it, you're done. The first character is a B, delete it, move forward until you see your first A, put the B there.
Oh yeah. Yeah.
that's really efficient.
That is very efficient.
Yeah. And it doesn't matter where the head is at the end, right? As long as you're in an accepting state. I also had another dumb question. If you suppose you want to erase a certain section of the string, like, is it it's not acceptable to just like write a blank here and leave the head to the right, right? And to pretend like, well, since there's a blank here, all these others are erased.
Yeah, that is a very interesting way of putting it. It's a very C with a null.
Yeah.
A null terminator, kind of like
Right.
strings are just, you read symbols and see until you see a null. It doesn't matter what's allocated past there.
Right.
That's the end of that string.
Yeah. So we do, if we want to erase a chunk, we have to like write blank, write blank, write blank. Right? That's
You could reasonably have some kind of system that says that anything that's written on the tape past the section that the read-write head is focused on is junk. But then you'd need some kind of garbage collector to come turn those to, we're at the inefficiency of Java levels now.
Yeah. The Turing garbage collector. There's a master's thesis for you.
Does that work for people? Do we want to actually see this drawn out as a program? Do we want to come write the transitions for what they have? Remember that if you volunteer to do any board work, this is recording and going up on.
Oh yeah.
That's something that you would agree to if you.
Okay. I mean, I'll give it a shot, but I'll probably need help from the audience.
Yeah, sure.
Okay.
I think this is where learning truly happens. I mean, that's true from the teacher's perspective as well. You learn it best if you're in charge of it and you get assistance as needed.
Yeah. Okay. Right, so I think the first state, we'll just assume we want to delete the B's, right? And the rules for that are if you read an A, right, a blank, and then it doesn't really matter where you move. You go to
I think the right is going to be in the right hand side instead of so if you input as the character that you see there on the first tape.
in the state, right?
And the state,
Right?
yeah, it's a state character.
Right,
Is to
blank,
I think you want state
state,
and then right and then move.
okay. Matter where we move.
Yeah.
Okay,
Nice.
now, that I know how to do the rotation.
I appreciate states that have names.
Yeah.
It's already a mile above anything we've done this quarter.
If I didn't name them, I would lose track of where I was. It'd be like Q what? Yeah. Okay. So if the first character isn't an A, we're gonna scan for an A, but I should have that as.
It should be the
the
starting
state,
state, so you're gonna have to set it as DEL_A.
Del A. If we read a B, now, well, we can erase, but we're also going to start scanning
Yeah.
for the A. Scan A, erase, move right. And then it's pretty simple as long as we're scanning for A's.
Yeah.
Two rules. We see a B, keep scanning. We also write a B, right. But if we see A, then we can halt. We write B because we had removed one B already. Doesn't matter where we move, but we're done.
Oh, we do need one more case because, actually we don't, yeah, because then if we just have an empty character, the entire string is set of Bs. But then it's not the same.
We should accept on that, right?
Well, we shouldn't accept on that because now we have a string that has one less B. So we need to add a B at the end.
Oh, okay. Yeah.
Yeah,
So
I didn't think about that until it was like writing it out. I was like,
blank. Then we should halt, write a B. Does man remove all move left?
Sure.
I think that's relatively complete.
Yeah. Does it
90%
work
sure.
on the empty string?
Um. No. Oh, it doesn't.
Well, it doesn't need to do anything on the empty string, right? Or does it needs to
Correct.
accept
It
it?
would- Yeah, it needs to define a halt. But it would also just be fine to not do that, or to just, it would immediately halt. There's no acceptance or rejection. This is something that the output of the tape is correct. So if we halt without making any change, then what's on the tape is already.
Yeah, then it doesn't matter because there's no transition on
Correct.
on an empty
So
character.
we actually don't need to define it, but if we did, it wouldn't be the end of the world.
Yeah.
Yeah, so that is an unnecessary transition that wouldn't break anything by including it.
Great. Very nice. Only, well, 5 necessary states.
Yeah. 5 necessary transitions, 3 states.
Oh yeah, 3 states.
Delete, scan, and halt.
Yeah.
Nice. Any questions on that from anyone? I buy it now.
If we were wanting to break this, the output to a second tape, how do we represent that in the transitions?
Yeah,
Oh yeah.
so we have 2 options. Whenever you have a 2-tape machine, you have to define whether you are referring to tape 1 and then tape 2, or you're referring to the reads of tape 1 and 2, the writes of tape 1 and 2, and the moves of tape 1 and 2. And that's true in the input as well, is that you have to state that here is the state that we're in. Here's what we're reading on tape 1, here's what we're reading on tape 2. So there's a 3 tuple as input, and then a 6 tuple as output.
Yeah, I thought it was like, if you wanted to do 2 tapes, you could just be like, so this is the first tape input, second tape input, and then this is first tape output, second tape output.
5 to
First machine move, second. I
Yeah.
think that's how I did it on the homework, so.
Yeah.
Yeah, I know in JFlab, when you're using like the designing the state diagram, it has them right next to each other, so it'll have all of what tape 1 is doing, followed by all of what tape 2 is doing.
Yeah.
So.
That is the standard, but I also don't pretend to care enough. If you come up with an equivalent notation, it's an equivalent notation. I do not hold you to the book's notation on.
I think I actually wrote my Turing machine descriptions as a table of like state, input, and then like empty rows of the table were just undefined rules.
Right. Other questions for, I do have another Turing machine problem, but we also have about 1 minute left, 1 or 2 minutes left. So it's probably not wise to dive into the next one, but maybe I can reveal it and have you think about it between today and tomorrow, in addition to what we can cover.
Bring in.
I think we're gonna have the space, this isn't gonna write over anything. Turing machine to add 1 to a binary number.
Oh. I have to carry the 1.
That's fun. Okay.
So we'll have a little bit of time to think about it. And we'll come back tomorrow and write this out on the board, talk about it in a lot more detail, talk about what we can cover that would be useful to all of you. As I think we're all seniors in here. Just about, if not, just about to that point. And so you're really thinking about the job market, reflecting back on your education here and thinking about what's missing.
I actually started my degree in 2017. There were long periods of time where I was not going to school.
Yeah,
We're back.
COVID. I don't
Yeah,
blame
COVID.
anyone over COVID.
COVID. was-
Having experienced that, I don't know who learned what over COVID. I don't know what extent that was actually possible, but maybe that's just me teaching discrete 8 a.m. over COVID.
Yeah, I did. I took a couple online classes from Eastern, and they were pretty easy. I think I took like networks and secure coding and a couple others, and it was like, I didn't really learn to the same level of depth as the other ones.
I think that's part of what's going on with our job market out there right now, is that there are a lot of potential employees floating around who aren't really great fits, especially, and they're still getting over the COVID hurdle of when you're hiring a new grad, are you hiring someone who missed a bunch of outcomes from COVID, or are you hiring someone who has the historical level of preparation? That's something that now you have to convince your employer of in ways, right, that you didn't have to before. Just kind of garbage. Any first thoughts of what we want to cover as we start packing up? Anyone want to just throw something out there that might, if we run out of time tomorrow, we probably won't. There are a few problems, but
I mean,
I
I've
can start
always
thinking about preparing.
wanted to make a programming language, so studying compilers is interesting, but also like interpreters, like if that's easier at all to build your own interpreter. I had gotten like 90% of the way towards making my own Lisp interpreter at one point. I just couldn't get the garbage collection. There were just bugs in it that I
Yeah.
couldn't figure out.
Yeah.
So making an interpreter, I think, would be super fun. Just or any learning towards
It's basically the same thing.
Yeah.
It's just that it is working with you line by line so that instead of basically halting at some point and saying, we broke here, you're partway through your computation. And so you can see a bit more with that. I actually have a video I can show people. It's like a 3-minute video that's about the differences between those.
I don't know how long this would take, but we could talk about like the benefits and disadvantages of implementing certain things in like a compiler as well.
Okay.
Like, design decisions or I guess features as well along with syntax. I know that they're like mostly the same, but that'd be interesting to see.
Yeah. We'll meet back here tomorrow.
Awesome. And Thanksgiving break starts on Monday, is that correct?
Or we technically have class Monday, Tuesday,
Oh,
and then, yeah, you're off Wednesday.
Wednesday,
I think I'll get a whole week.
I